Okay, welcome everyone to Maine Climate Table's first webinar of 2021. Let me just do a quick sound check with Katie, my colleague at the Maine Climate Table. Katie, can you hear me okay?
You sound great.
Okay, thank you for that. Good to have everybody with us today. I guess one of the big advantages of COVID is that we've realized we're all just a Zoom click away. It doesn't matter whether we're down the street in Brunswick, Maine, or in Fort Collins, Colorado. We're all just a click away. So I was reading an article about the rate of the Greenland ice sheet melt last December and came across the name of Dan McGrath. Looked him up at Colorado State University and saw all the great work that he's done on the cryosphere, part of the Earth that stays frozen, and invited him to join us today in Maine. And since it's winter in Maine, we should be talking about the cryosphere, the part of the Earth that stays frozen year round. So there's Dan. I'm going to introduce him in just a minute. We're going to do something a little different this time with our webinar, rather than just having the traditional 40-minute seminar. I'm going to have a series of questions for Dan. It'll be, for those of you who know Maine Calling with Jennifer Rooks. I'm no Jennifer Rooks, but anyway, it'll be sort of an interactive session with Dan. And so before I introduce him, probably most of you know by now the Zoom routine, but there should be a Q&A button at the bottom of your screen. And if you've got a question for Dan at any point, just type it in the Q&A box. And Katie, my colleague at Climate Table, will help help ask the questions of Dan as we go through various topics. So take advantage of the Q&A. How often do you get to talk to somebody who studies the cryosphere? You might not meet anybody again this year that can answer your questions. So ask them while you can. So now on to Dan. I mean, as an ecologist, I've been to some pretty amazing places on the planet, but Dan has me beat by a long shot. He's been to Greenland and Antarctica and South Georgia Island and Patagonia, and now he's studying ice and snow in the Rocky Mountains. Somewhere, Dan, I saw Alaska in there too, so I think you've been to Alaska. How could you not go there? He's got a PhD in environmental sciences and geography from the University of Colorado, down the street from him in Boulder. But he really became famous when he got his undergraduate degree in geology and environmental studies from Bowdoin, I think back in 2006. So Dan, welcome. We're glad to have you back in Maine, even if it's just virtual, to bring us up to speed on what's up with the cryosphere. But maybe before we get into the science, and I'm looking forward to that, how did you end up at Bowdoin, of all places, and where did you come from, and how did you end up in Maine, and why didn't you stay in Maine?
Yeah. Thanks very much for the invitation and the opportunity to join you today. It's really my pleasure. I guess I've been fascinated with the Earth for a really long time, and I think unknowingly with the cryosphere starting at a really early age. I think my dad brought me winter camping for the first time when I was 6 or 7. I think it was something like -30. And I think he gave me the warm sleeping bag, and as the story goes, he shivered the whole night in the rental sleeping bag that night. But then I was the kid building snow caves on the front lawn and trying to convince my parents to let me sleep in them with my friends. And so I've really had this passion for studying the Earth for a long time, and Bowdoin was a really natural fit for me.
And it was a great program for you, from what I hear. It was the perfect fit.
Yeah, absolutely. I have this distinct memory, actually, as a freshman, of wandering around the Perry McMillan Arctic Museum on campus and just being enthralled with the historical artifacts that were present there, the stories of exploration of the heroic age, Shackleton and Perry, and in particular this section of an ice core. I don't know if it's still there in the lobby of the museum. The story that goes with it, that the fact that the ice core can record the Earth's climate in the past, the greenhouse gases, the composition of the atmosphere. And I found this really obviously fascinating.
Mm.
At the same time, that when I was at Bowdoin, there was just a lot of popular press on climate change and changes in the polar regions. In particular, there's two reporters, Elizabeth Colbert and Andrew Revkin, that had a really big impact. I mean, I remember these articles about the polar region and documenting the changes there, and I was like, this is what I want to do. This kind of wild adventure of getting to travel and live in these pretty remote parts of the planet, and then conducting research that hopefully has an impact on society.
Mm.
I guess at Bowdoin, the amazing faculty there, and in particular, there's one faculty member, Colin Rossler, who I really owe a huge debt of gratitude to. She taught a class called Poles Apart, which was comparing the Arctic and the Antarctic, and really has been an inspiration for me throughout my career. And through her and connections with Don Perovich and the Cold Regions Research and Engineering Lab, I got to go up to Barrow, Alaska, as a junior and conduct research on sea ice up there. And it was really, amazing part of my undergraduate experience.
Mm. I was just looking to see if she might be in the panelists right now. I know we've got some Bowdoin folks with us today, so that's great. And we may have met because my office was down the far end of Main Street when you were at Bowdoin. So we probably crossed paths a couple of times in those years. Let's see. So maybe can you give us an overview before we get into slides that I know you've got? But what range of things do you study about the cryosphere before we go a little deeper into the weeds?
Yeah, so I guess broadly speaking, I am a cryospheric scientist, meaning I study the frozen parts of the planet, and that can be ice sheets and glaciers and seasonal snow and permafrost and sea ice. These all the various components of the cryosphere. I guess more specifically, I am a glaciologist, meaning that I study glaciers and ice sheets, and really their response to climate is the area that I've focused. But as is the case for many aspects of the Earth system, it's an interconnected system, and you can't study a glacier in isolation and not consider what the atmosphere is doing, or consider, for an ice shelf that's floating on the ocean, you need to know something about the ocean and ocean circulation and the impacts that will have on the topic that you're studying. So really, it's a really interdisciplinary field and requires collaboration with scientists from a number of different fields. I can very quickly get over my head in talking about ocean circulation, and that's where I just defer to someone who actually truly knows the details of that field.
Mm-hmm. But ice is your thing, pretty much.
Ice is my thing, yeah.
And snow.
Snow, yeah. I guess recently, living out here in Colorado, and just the value of snow, both economic and just true as a water resource. Snow is really important here in the West. And we don't at present really have a great way of measuring that from space. We really want to have a sensor that we can put on a satellite that's in orbit, that's measuring the amount of water that's stored in the snowpack. And in recent years, I've been part of a number of NASA-funded campaigns trying to do that, to basically test a variety of methods for measuring snow water equivalent.
Mm. So let's talk, maybe you can define mass balance for us, because I know that's important. And one of the papers I just read in preparing for our conversation today was one about the loss of ice. And I think they said they estimate 28 trillion tons of ice has been lost since 1994. Who can even get their head around a trillion tons of ice? I mean, I don't know what that means. It sounds like a lot.
Yeah. We use gigatons, and that is no more useful in trying to convey the actual significance of a gigaton. But a gigaton is a cubic kilometer of water, which starts to feel a little bit more like you can wrap your head around that. A kilometer by a kilometer by a kilometer, that's a gigaton in terms of its mass. And that, I think, is the equivalent of filling something like 400,000 Olympic-sized swimming pools. Mm-hmm. So when we say the Greenland ice sheet's losing, 300 gigatons of ice per year, that's 300 cubic kilometers of water that's being lost from the ice sheet each year. And each one of those cubic kilometers is filling 400,000 Olympic-sized swimming pools. Mm-hmm. I often try to get an analogy of, a nearby sports stadium and say, oh, fill that X number of times. And that X tends to be a very large number when you start kind of converting the mass losses from glaciers and ice sheets into actual volumes that we can kind of wrap our heads around.
Mm-hmm.
But yeah, I mean, mass balance more generally is just, understanding kind of the sum of the inputs, which is generally snowfall on a glacier, and the losses, which is going to be the melt, or the term that we use is ablation. So the melt of the snow and ice that subsequently runs off from the glacier. Oftentimes, for our bigger glaciers that terminate in the ocean, or are kind of glaciers that are flowing off of the ice sheets, there'll be an additional components of mass loss where they'll calve icebergs, and they'll also melt from the bottom side, something we call basal melt. So the floating extensions of the ice that are sitting in the water can also melt, quite easily in the water.
And we'll go to your slides in just a second. I'll put one more question about, I was surprised to read how hard it is to know the thickness of ice. I think people like me would assume, okay, you know how thick it is to the foot, but it's not quite that simple, right?
Yeah, it's a lot harder than that. I actually remember really naively walking into my first couple of days of graduate school, walking into the office of my advisor, Connie Steffen, and he was like, so, what are you thinking of working on? And he's, been working in Greenland for years and years. And I walked in there and was like, I'm going to measure the mass balance of the Greenland ice sheet, and he didn't laugh like directly in my face, but was kind of like, yeah, I mean, me too. Like that is kind of the holy grail. That's what we're really trying to do, is both understand the mass of these ice sheets and glaciers and how they're changing, and the processes that are driving it. Have any sort of understanding, predictive ability into the future of saying, okay, how are these glaciers and ice sheets going to evolve in the next 10, 50, 100 years? We need to really understand the processes that are controlling their mass balance. So it's not just a matter of measuring the mass balance, which is a hard thing to do, but we also need to understand the processes. And actually, maybe I can share my screen. I have a little slide on that very topic.
Yep, good. Go right ahead.
See how this works here.
Mm-hmm.
Okay, can you see my slide now?
Sure can.
I guess this is just coming back to Bowdoin and just kind of the connections here. Obviously, Bowdoin has a lot of polar connections, and Robert Perry pictured here, the polar bear, and this is actually Bowdoin Glacier up on the northwest coast of Greenland near Thule Air Force Base, and then just a little comment there on Colin and the class poles apart. Coming ahead to components of mass balance, this is just a little diagram here that I think that shows us pretty nicely, where we have our snow accumulation in the upper part of the glacier, and then melting being the primary process that's losing mass for these small alpine glaciers. But this is coming back to measuring mass balance. We wish we could pick up our glaciers and ice sheets and put them on a scale. That's what we're trying to do, is, do that through time and basically measure how much they weigh. But obviously that's not possible. So we rely on a number of different approaches. Some of them are, relatively simple, of going out and putting stakes on a glacier and coming back to those every, 6 months or every year, and measuring the relative changes in snow and ice at that location. And a lot are a lot more sophisticated and are increasingly being done from a satellite-based platform. So a number of different approaches are being shown here. We have really highly accurate lasers, that are orbiting at 800 kilometers above the Earth's surface and are measuring surface elevation changes of a few centimeters through time. Or on the right here, these GRACE satellites are actually two satellites that fly in tandem in orbit. And the distance between them changes, by millimeters, essentially, as the gravitational field changes on the planet. As you reach a spot with more mass, there's greater gravitational attraction, and the satellites separate ever so slightly. And so tracking that distance through time, you can invert that and get at changes in the mass of the planet and how that's changing. And so we have a lot of tools to do so, to better understand. And I think, this next slide, I try to highlight some of the changes that are happening. These slides, and I'm not going to, we don't need to squint our eyes too much, but basically On the left here, we're looking at mountain glaciers. On the top right, we're looking at Greenland, and the bottom here, Antarctica. And the simple message is that all of these, are losing mass, and they're losing mass at a pretty significant rate, on the order of 250 to 330 gigatons per year. So collectively, we're at almost 1,000 gigatons per year, or 1,000 cubic kilometers of water are being lost from our glaciers and ice sheets each year, which it seems very abstract. And I just want to show a video here. This is a time lapse of Mendenhall Glacier that Jim Baylog and the Extreme Ice Survey put together. And this is, I have tens of these. He's produced these from glaciers all over the world. I've taken part in some of those efforts in Antarctica and South Georgia Island. These are not cherry picked to be like, oh, a glacier is losing mass, let's take a photo of it over time. Like, this is just meant to kind of help kind of ground these satellite-based observations. Like, numbers are what we need to truly understand how the planet's changing. But I think these visual images really do a nice job of conveying some of that, what that change looks like. And this is just over a 5-year interval of Mendenhall Glacier near Juneau. Fortunately, in our current climate, it's not possible to do this. You can't play in reverse right now and get the glacier to come back to where it was.
Dan, can I just, while you're showing that, one question that came in, is there a way to translate the volume you just said that we're losing each year? I forgot, how many gigatons did you say?
Yeah, I think it's somewhere 800 to 900 gigatons per year across all of the.
So is there any way to convert that to amount of sea level rise? And I know those millimeters, or maybe even a fraction of a millimeter.
Yeah, you're going to test how I remember numbers. It's 300 gigatons of ice is roughly a millimeter of sea level rise. So we're roughly seeing 3 millimeters of sea level rise per year from the ice sheets and glaciers combined.
And that's at the rates of the last couple of decades.
In the last decade, roughly. Would be about 3 millimeters, which obviously doesn't sound like much. You're like, 3 millimeters, so what? 3 millimeters every single year and at an increasing rate has huge impacts. And I think as you've seen of this so-called nuisance flooding along the East Coast, in Florida and other kind of low-lying areas and places like Bangladesh, a few centimeters over time, or, now we're looking at, 20, 30 centimeters over, a longer period of time. Like, that's really significant, especially when coupled with storm surges. I think that's where the impact is most significant, is when you have, this already rise of, sea level associated with the, low pressure system and the storm, combining that with this long-term change in sea level, you can have really, really significant impacts.
And another question that came in, those satellites, I think the GRACE ones that you talked about, they can't tell the place of the rock surface underneath the glacier, can they? Or
no, so without getting into too many details, they have very coarse spatial resolution, meaning that like the footprint of that they're observing is fairly large, on the order of hundreds of kilometers of a length scale. So they're just basically detecting changes in mass, but they're hugely important for studying groundwater depletion. In India and elsewhere, these satellites have been used to track changes. California as well, to track changes in groundwater, because it's just, you're taking mass that was there in the subsurface and you're, depleting it, using it, and it's running off to the ocean or evaporating. You can detect that change in mass really significantly. And there's hundreds of scientific papers using GRACE to do that. And we're now on the GRACE follow-on. Just recently, in the last couple of years, they're kind of the next generation of these satellites were launched.
So I was going to ask you about the benchmark glaciers next. Do you have slides about that, or can you explain what the so-called benchmark glaciers are?
Yeah, I have one slide here that would be helpful, just from a recent paper that that our group co-authored. So the benchmark glaciers, I guess, are a series of, I mean, rather than show another graph, I'll just put a pretty picture up while I talk about them, I guess, and we can come back to that graph after the
All
fact.
right.
This is Wolverine Glacier. This is a spot in Alaska on the Kenai Peninsula where I've spent a lot of time in the last 5 or 6 years. It's been one of these benchmark glaciers, meaning that they've been studied for a long period of time. It's a name that the U.S. Geological Survey has given 5 glaciers in the Western U.S. There's one in Washington, one in Montana, and then 3 in Alaska that have been studied since the 1950s and the 1960s. And, you know, in the grand scheme of things, that's not a very long time, but in terms of a continuous mass balance record of glaciers, this is the longest, some of the longest records we have globally, and definitely the longest records we have here in the United States. And they give us this really unique perspective on understanding the connections between climate and glacier mass balance. You know, when you're measuring it year after year, season after season, you can understand how, you know, there's how natural variability, you know, Pacific decadal oscillations and changes in atmosphere, you know, patterns, you know, from year to year can influence the mass balance of these glaciers. And we can start to really see that in these records. And so the real power of these records is their duration. The fact that, you know, we have 50 plus years of understanding and measuring their mass balance. And, you know, the changes are really significant. Without going to too many gory details here, basically the y-axis on each of these figures is the cumulative annual mass balance in meters of water equivalent. But basically what this is saying is that, say this is South Cascade Glacier in Washington, it's basically lost 40 meters or 130 feet of water from its entire surface in that 55, 60 years. So every year it's losing mass. You know, this green curve is tracking the annual mass balance of that. And over time, when we integrate that, it's a huge amount. You know, it's 130 feet of water have essentially been removed from these glaciers. And I don't have before and after photos here, but if I had included them, you'd be amazed. You know, it's just, they look like a defeated, deflated version of their former selves in the 1950s and 1960s. There are really significant changes are underway on these glaciers, and these records allow us to document that. And it's being done in a couple different ways. You know, we're obviously the USGS teams out there every single season measuring these stakes that are distributed over the glacier surface. But increasingly, as I alluded to, we're using satellites to measure their mass balance. And so we produce from stereo optical imagery, so just visible imagery from a satellite, when it's shot from one perspective and then shot from another perspective, those can be combined with kind of photogrammetric principles to produce an elevation model of that glacier. And by doing that repeatedly through time, you can basically track how the elevation or the volume of the glacier has changed. So it's just another tool that we use in tracking the mass balance of these glaciers.
Mm-hmm. While we're on I guess maybe talking about mountain glaciers as opposed to ice sheet glaciers, if I've got the terminology right, the mountain glacier, like the ones in Colorado, I guess, or do you have glaciers in the Rockies, or is it just further north?
Yeah, we absolutely do. That they're, you know, my career, hopefully my career is not following the same trajectory as the glaciers that I study. You know, I started in Greenland and Antarctica, I then moved to Alaska to work on these, you know, pretty real glaciers. And now some recent work, I've been studying these dinky little glaciers here in Colorado that they're borderline real glaciers. You know, for it to be a glacier, it has to flow, to form under its own weight. Essentially, that's kind of a defining characteristic of a glacier. And we have some that are doing that, but they're pretty modest in size. But it's really, scientifically, it's actually, I find it really fascinating because obviously it's, you know, kind of a space for time substitution, something you're probably familiar with in the ecological field, you know, where it's like we can say something about what Alaska might look like in 100 years. And really the questions I'm asking here in Colorado are, what does it take to actually get rid of one of these glaciers from the landscape? Because as they get smaller and smaller, they retreat into these really favorable locations where they get avalanching on them or they get extra wind redistribution. Like here in Colorado, they're all kind of on these high elevation north to northeast facing cirques where the winter winds just kind of blow snow off the divide and plop it right on top of them. So while we might get 3-4 feet of snow at that location just in a kind of normal year, the glaciers have something like 40 feet of snow on them. We'll have used radar to image that seasonal snow thickness, and they're just vastly thicker in terms of how much snow gets deposited on them because of wind deposition. So it's an interesting question as well.
Mm-hmm. So just hanging on to the mountain glaciers for a minute, can you say a little bit about how important they are for sort of the human dimension and the water supply globally? It's my understanding that they're critical in some parts of the world, and that there may already be a water supply problem. I don't know. Could you say a little bit about the role in fresh water supply for humans?
Yeah, in particular in high mountain Asia, glaciers play an incredibly important role in as a water resource, where they help offset maybe a dry year. You'll have more melt in the glaciers, and they'll keep the streams flowing at a reasonable level, keep the rivers, flowing. And so in that region in particular, and if I jump back 2 slides, let's see here. Yeah, this one actually, the figure on the right does this pretty nicely. Basically, in these pie charts here, the bigger the blue component of it, the more important glacier and snowmelt is to the stream flow in that location. And so in isolated basins, here in the Western US, obviously, where snow is incredibly important, in the Andes, there's, individual basins where a glacier may have a really important role in delivering water resources for a city downstream. But really, it's basically all of high mountain Asia is really dependent on glaciers and seasonal snow melt for keeping their rivers flowing. And so if we were to look into the future, many of these locations around the world, there's something we, much like people use peak oil to kind of define when peak extraction would occur, you can talk about peak water as well coming out of these basins. Basically, as this analogy may work in this context, you can think about a glacier as your checking or as your bank accounts. You have your savings account, which is basically the volume of the glacier. The ice that's stored there is your savings account. Each year, you operate out of your checking account. You deposit money in when you get paid. You take money out when you buy something. If you spend more money than you make, you need to cut into your savings account, and basically your glacier shrinks. And so what's happening around the world is as we deglaciate, as these glaciers lose mass, they're shrinking, and basically we get that dividend. You can live life very luxuriously when you're just extracting money from your savings account. And that's essentially what's happening in many basins around the world, is as the glaciers deplete, those savings accounts are being drawn down. At some point in the future, that savings account won't be there, and you won't have that kind of surplus of water that might be seen at present. And so it's something that's studied quite closely, because if you look at it just for a couple of years and you're deglaciating a landscape, you might say, oh, wow, there's lots of water here. But that water's only there because you're melting stored ice on the landscape.
So it's something we should be worried about in terms of a warming world, the loss of fresh water.
Yeah, absolutely. I mean, I would move to Maine. It's a great spot to be for future concerns to fresh water. That's probably very low on kind of climate change related concerns in that region of the country. Here in Colorado and other parts of the West and high mountain Asia, it's a really significant concern.
And so maybe one more question on the mountain glaciers, because of what happened. I think last Sunday, the dam that burst in northern India, and at least some of the reports I saw suggested that it was because a chunk of glacier broke off. But I don't know whether you know what happened or not, or everything in the news may not be exactly how it is, but there's a physical thing that goes on as the glaciers retreat that you were explaining to me last week. Can you explain what that is, and maybe that's what happened. I don't know, or maybe you
Yeah,
can speculate.
Somewhat speculation at this point. I mean, I think there's increasingly some clarity coming through of what exactly happened in this event in particular. As glaciers around the world retreat, a whole series of associated hazards are being born. Essentially, one of the biggest ones are these glacial lake outburst floods, where as the glacier retreats, you may pond meltwater kind of in a receiving basin near its terminus or near the toe of the glacier that's being dammed by either bedrock, another glacier, or by the moraine, basically the sediment that the glacier deposited there. And those can burst, drain catastrophically, creating huge floods. It's my understanding that's not what occurred in this case. There's no evidence that a glacial lake drained here in this event. It's more likely that we're seeing some sort of mass movement that the glacier likely took part in. Glaciers and a lot of the landscape are being held together by ice, and it's at this 0 degrees C threshold, 32 degree Fahrenheit threshold. And it just takes a little bit of warming to get to the other side of that. And essentially that glue can come undone. And we're seeing increases in rockfall and mountain ranges around the world, increases in these mass movements. In this case, it seems like there was a detachment of the glacier itself, a mass of the glacier became part of this mass movement. Again, a little bit of speculation here, exactly what happened, but this is not in isolation and is not unexpected, I guess, is the fact that, we're removing the glue from the mountains in many places, and the impacts are really significant. And I expect that we will continue to see events like this that have huge impacts on human life and infrastructure.
So maybe back to Greenland for a minute. I guess the question I posed in the advertisement for your talk today was, just how much water is there in the Greenland ice sheet? And if it all, I know it's maybe a hypothetical question, but if it all melted, how much would the ocean rise?
Yeah, there's roughly 7 meters or 23-ish feet of global sea level equivalent stored in the Greenland ice sheet, which is a really big number. You don't want to think about 23 feet of sea level rise and what that means. And I think it's great to know that volume and like that's important, but I don't like to use that too much, just because I think people then are like, it belittles, maybe the millimeters of sea level rise we're talking about. And in reality, if we're going to see 30 centimeters or more contribution from Greenland by the end of the century, that is a really big deal. And I want society to focus on that number, because 30 centimeters, when coupled with Greenland or coupled with the mountain glaciers and coupled with Antarctica, we're looking at 1 meter to 1.5 meters of sea level rise. Like that's a number you should be scared of. 7 meters, that's just like out there as some big number. It's the 1.5 meters that we should all be really worried about, because that's what's coming. We're already committed to that level of sea level rise. And what we need to do is really limit further contributions to that. And it's not that far off. There is a great recent publication, if I can get my mouse to behave, here. And this is looking at basically the evolution of the Greenland ice sheet over the next 1,000 years. And if we just look at this middle panel here, I don't know if you can see my mouse here, but B, this is basically under RCP 8.5, which is the high emissions scenario. By 2700, the Greenland ice sheet has largely deglaciated. So it's not like 7 meters is something that's not going to happen. It's just out there, hundreds of years into the future. Unless we obviously don't follow the track. I mean, I think this alone is a great argument for, you should advocate very strongly for being on RCP 2.6 rather than RCP 8.5. That's the difference between 7 meters of global sea level rise, essentially.
And probably everybody knows about RCPs, but the lower emissions future would be RCP 2.6. And I think that's in like watts per square meter or something like that, as I remember. And RCP 8.5 would be a much higher emissions rate. I guess business as usual.
Yep.
throughout the rest of this century. So I hadn't seen that before.
Yeah.
And about the physics of how does ice melt in Greenland? Is it more air, the air above, the water undercutting glaciers, both? Physically, how does that take place?
Yeah, in Greenland, it's roughly split between melt at the surface and iceberg calving. You know, it's this basically this ice discharge component. If you speed up a glacier and it's flowing faster and more ice is being discharged to the ocean, it's obviously losing mass from the glacier or the ice sheet itself. And for Greenland, it's roughly this 50-50 split. It changes from year to year. I can try to, let's see if this video will play to give you a sense. This is from 2012, which was an incredibly large melt year. This has volume. I don't know if volume's going to play, and the volume is disturbingly loud, generally speaking. So I'll try to turn it down on my computer. I don't think that's going to do anything for everyone else. So just slight buyer beware here.
Mm-hmm.
So that's the Watson River. That's on the east coast. Sorry, that is on the west coast of the Greenland ice sheet near Kingaluswak. And this is not from this flood is not from like a glacial lake outburst flood or a sudden discharge. This was sustained discharge in late July, I believe, in the summer of 2012, when we saw just an incredible amount of melt on the Greenland ice sheet. And just as as a graduate student, I spent a lot of time living and working on the Greenland ice sheet. This is our camp, which was affectionately known as Swiss Camp for the Swiss team that first built this camp in around 1990. And one of the weather stations that we spent a lot of time monitoring and working with, we had at upwards of 18 or 20 weather stations all across the ice sheet that are still operational today that kind of give us this long-term record of the climate there. But this looks like the camp's doing just fine. You would say, oh, wow, you'd be concerned it might actually be starting to get buried. In reality, when all this snow melts, things like this can happen. So basically, this camp was installed at what's called the equilibrium line of the glacier. It's the spot where the amount of snow that's being added to it is supposed to balance the amount of snow and ice that melts the following summer. On every glacier, there's a theoretical equilibrium line, and it moves around in time, but that's a spot that should stay at relatively constant surface elevation. But as the climate's warmed in Greenland and as the equilibrium line has gone up in elevation, Swiss Camp has very firmly found itself in the ablation zone. And so we went up there, obviously in August of 2009, to rebuild the camp. We did not expect it to look like this. We expected it, we were just going to re-drill the posts in and kind of maintain it. And we got out of the helicopter and it looked like this. And it was, after a month of pretty hard work, we got it back to looking fairly reasonable. But as you might get how the story goes, it's basically not sustainable at this location. It's in the ablation zone. The equilibrium line has gone way up in elevation, and Greenland's just losing 300 or 250 gigatons of ice per year. And this was, as a graduate student, this was a really, pretty visible evidence that the climate was changing and that the Greenland ice sheet was changing in a very dramatic manner.
We're incredibly rapidly running out of time, Dan. So hang with me here. And Katie, if you can still hear me, I'm watching the questions and trying to ask them as I can, just to save time.
Thank you.
Dan, one of the questions, and I don't know that you'll get this one, but someone wanted to know how many gigatons of water are in Moosehead Lake, Maine, which is our largest, and I don't know either. And
yeah, that'd be a great thing to calculate. If I had time yesterday, I was gonna convert that 845 gigatons to the state of Maine and just what it means in terms of thickness of water on the state. But
Right, or ice. Yeah. Well,
my guess, it would fill Moosehead many times over.
many times over,
Yeah.
my guess too. But we'll work on that afterwards. Let's see. Maybe because Dan's got to go to class at like 10 till. So I got to let him go in a few minutes. But could you,
John? I'll stay and you can give my lecture. I'd be happy.
well, I would love to do that, but students wouldn't appreciate it. So maybe switching to the Chasing Ice project that you were a part of 7, 8 years ago, I can't remember. And I can't remember the guy who did the name of the guy who did that incredible movie, but it obviously engaged the public in a way that scientists would have a hard time doing. Can you say a little bit about that, the Chasing Ice video, and we can put the link, maybe Katie can find the link, or we can put it on our website, the Chasing Ice video. Tell us about that.
Yeah, I recognize at a pretty early stage in my career that outreach efforts and kind of communication with the general public is going to have a much bigger impact than any single kind of peer-reviewed scientific publication that I write. That's a conversation between me and the hundreds of other scientists that are working on this, not the billions of people that live on our planet. And so it's actually, I should fly back to this first slide. When I was putting this together yesterday, this article by Elizabeth Colbert, the Climate of Man in the Atlantic, I highly recommend it if you've not read it. It's obviously pretty dated at this point, but it was really impactful to me. I found a very foreshadowing that actually this photo here was taken by James Balog, who's the founder of the Extreme Ice Survey and the individual featured very prominently in Chasing Ice. This is way back before I knew who James was and had the opportunity to work with him. But Extreme Ice Survey and Chasing Ice are a really wonderful example of this outreach effort, that you can bring something that's really far off, really far away, these changes that are hugely that are really significant and hugely significant for you, even though you don't necessarily know that. And it really brought it to everyone's television, and it brought it in a way that was really effective, in my opinion. And it's something that I think is essential as a scientist, is doing that, is participating in these outreach and communication efforts to explain the science that we're doing, and help kind of convey the information that we're finding.
So you helped out on, did you find glaciers or the right spots that were good for Chasing Ice, the movie, or how did you?
For Chasing Ice, it was more advising, and in subsequent years, in 2016, 2017, around that time, we spent time down on the Antarctic Peninsula and on South Georgia Island, where we deployed another, I think at one point we were up to about 15 cameras down there on glaciers in these locations. And so I was really heavily involved in that component of the project, of kind of having a Southern Hemisphere kind of footprint for this project.
Mm-hmm. Mm. And maybe I'm gonna maybe end on a few questions here, but I know that Conrad Steffen was your mentor for many years and died tragically in Greenland, I think last summer. I was wondering if you could just say a little bit about his legacy, his scientific legacy.
Yeah, Connie was, as we called him, and many call him that knew him well, was a really, really incredible individual. As you can see here, this photo I took in Greenland, I obviously had this legendary beard. I think he was also legendary in the sense, I've never met anyone who is like as impervious to cold as Connie was. He would work at a weather station and be, minus 20, bare hands, wiring, touching a metal screwdriver and wiring in these little tiny wires into a data logger. I got the opportunity to spend a lot of time with him in Greenland and Antarctica and all over the world, and really am grateful for the opportunities that he provided and the mentorship that he gave me throughout my graduate and postgraduate kind of career. And it's really fun actually having your PhD advisor this is me driving a snowmobile and I'm towing him behind me. It's I flipped the power relationship in that case.
Mm-hmm.
I had him behind me in this sled as we were collecting radar data. But I had a lot of fun with him in the field, and yeah, really incredible mentor.
Was he at Colorado State or University? Where was he?
University of Colorado.
Okay.
Yeah, during my PhD, and he's Swiss born and actually had moved back to Switzerland in 2013 to lead up a very large kind of environmental science organization, VSL in Zurich.
Mm-hmm. Mm-hmm. Okay, so maybe I'll use the last 3 or 4 minutes here to just ask some questions in the Q&A. Let's see, how was the snowpack in Colorado this winter? I don't know whether that's related at all to the fires going on out there, but I think you were explaining you were studying sort of the relationship between snowpack and fire.
Yeah, great question. In general, here in Colorado, we're slightly below. I think we're hanging out about 80 to 90% of the long-term average. Up in Wyoming and Montana to our north, they're doing better than we are this year. But I think, this, year-to-year variability is just part of the system. But I think when we look at this over a longer period of time, we are seeing very dramatic declines in the amount of snow that accumulates in the mountains. And if we just look at this figure on the right, basically red means that it's less, it's losing SWE, and you can see SWE being snow water equivalent, the amount of water that's stored in the snowpack. And it's changing in a very dramatic way across the Western U.S. And as I mentioned previously, the last couple of years I've been pretty heavily involved in this NASA SnowX project, which is really trying to test sensors that we can measure this parameter from space. Like all these measurements here, those red circles correspond to automatic stations, snow-tail stations that are throughout the Western U.S. and Canada and Alaska. But we want to be able to measure it globally, kind of, at higher spatial resolution than these stations allow. And so that's really the goal of this campaign. And yeah, here in Fort Collins and Colorado in general, as you might have heard in the news this summer, we came through a pretty horrific wildfire season. I mean, all of the West did, but hit really close to home here in Fort Collins. Mm-hmm. This is a photo of the Cameron Peak fire, which was burned, I think, something like 208,000 acres, the largest wildfire in Colorado history. And this is a view of the fire from 5-10 miles south of where I live in Fort Collins in Loveland. And the fire got pretty darn close to the edge of town. There's never any real concerns that it was going to burn Fort Collins, but it burned hundreds of houses and hundreds of thousands of acres of fire, and so of forest. And so I have been involved in studying the impact of wildfires on snow accumulation. Just through this, these are some drone imagery that we've been collecting up at Cameron Pass, which is just west of Fort Collins. Drones, we've not talked about them at all, but are really kind of revolutionizing a lot of aspects of geosciences. And here we're using them for something called structure from motion. So we just fly the drone in this gridded pattern over the area of interest, and each image has a lot of overlap with the one before and after it. And that overlap is the motion that we can then apply photogrammetric principles to and calculate the structure or the geometry of the scene. And so the top left here is just what we call an ortho imagery, but it's just an aerial photograph, essentially combining all those images. The bottom here is a point cloud, and I've kind of rotated it so you can kind of see it obliquely. You can see the burn area here where, obviously there's no vegetation, just the trees are remaining, trunks. And so this on the top right is the surface elevation product. So basically this is the elevation, and we do this repeatedly throughout the winter, and we can track the surface, or basically the snow depth, both in the burned area and the unburned area, and understand how the wildfire, basically when you lose the vegetation, the vegetation on the trees, you have less canopy intercept. So there's less snow that gets caught in the canopy, which is good in some ways, because then you have less sublimation, the process of this solid going to a gas. So you actually end up with more snow on the ground at times in the unburned areas. But then in the springtime, when the sun's really, high in the sky and there's lots of energy around, you don't have that shading effect of the canopy. So you're exposed to that full kind of energy from the sun, and your surface is really dark because you have all this, soot and ash on the snow surface. And so it absorbs that energy very easily. And so that in combination means that the snowpack will likely melt much faster in those locations. And so we're trying to understand how this plays out on different kind of aspects. So, if we're on a north facing versus a south facing, that's going to influence this as well. And definitely some really interesting. And if you think about how much of the West has burned in the last decade, really important questions to be asking, because a lot of our resources are tied up now in this burned area of the Western US.
Well, it's less than 10 till now, so I'm afraid I need to let you go, although I don't want to. But thanks, Dan. I guess there's a few more questions here, but we'll post some links to Dan's work when we post the recording of this webinar, probably within a day or so, links to Chasing Ice and maybe some of Dan's scientific publications, which I enjoyed looking at. So thank you, and come back to Maine, not virtually, sometime.
Yeah, I hope to come back soon. My I guess it would have been 15-year reunion was supposed to be this May, and that was canceled because of COVID. But I'll make it back soon, and yeah, I look forward to my next visit to Maine for sure.
All right, well, let us know. Like to meet you for real. So have a good class and the rest of the day. And for those of you who are joining us today, we'll be having another webinar next month on the rural-urban divide, more of a sociological kind of conversation. So you'll hear about it through email, and we hope to see you there. But Dan, thank you one more time for being with us today. It was great to have you here. And one of the upsides of COVID is easy to meet people like you. So thank you for the time and all the work you put into this.
Yeah, thanks for having me. I really, really appreciate it. It was a pleasure to join you today.
All right.
All right.
Thanks, everybody. We're going to sign off for now, and we'll see you next month. Have a good day.
Bye.